Okay, in this session we will be talking about one more case study here. This is about a phenomenon called glitching in pulsars. Okay, so this is based on this particular conference report. Suppose you are given this kind of data. There are two data sets, the top one and the bottom one. I will explain what these quantities are. But suppose somebody gives you this kind of data set and asks you whether this suggests multimodality of underlying probability distribution function, thereby implying multiple populations in the data. How would you look at it? That is the essential question. So, if you look at the top histogram, the histogram seems to show you two peaks, two peaked structures. Now, how seriously should one take it? That is the essential question. Two things are important when one is trying to gauge anything from histograms. One is that the number of bins should be optimal in some sense. We talked about this in one of the previous sessions. The point is, if you put all the data in a single bin, the histogram will look flat, whereas if you have too many bins, then you will see a lot of fluctuating kind of histogram, which also does not give you firstly a correct idea about the underlying distribution, and secondly, if you have too many bins, today you have this data realization, tomorrow you might have another data realization coming from the same system. Then if you have too many bins, then the histograms will look completely different. Whereas we will talk about this phenomenon in another session. If you have too few bins, then everything looks flat. Your histogram does not change much across data realizations, but then clearly it is not capturing the shape of the underlying probability density function. This is the catch here. So, let me assure you that in this case the histogram, all the histograms have been drawn with the Friedman-Diaconis prescription. So, it is as optimal as one can get. The next question is, you have these data points which are marked with little black ticks here on the x axis. How variable are these data points across different data realizations? That is another key question, because the dip that you see here, which is suggesting that there are two modes to this distribution. If the data points are too much variable, then in some data realization it might so happen that there is a crowd here, crowd of data points here, thereby giving a peak here, and this multimodal structure, apparent multimodal structure, will be completely lost. So, one has to worry about optimal binning of for the histogram, and secondly the variability in the data points. If you look at the bottom histogram, these two quantities are actually related. If you look at the bottom histogram, what one sees is there is some sort of a broad peak. If one has to take the picture seriously, this might suggest multiple populations also. When I say multiple populations, it is in the same sense that if you consider let me give an example from common ordinary life situations. Men and women have got slightly different height distributions. Both are individually normal, but if you take the entire population as a whole, then the two distributions mix and you get something that is what is called a mixture distribution of two Gaussian components. Again, this is something that we will be talking about later on in this session. So, you do not have a single Gaussian, you have two Gaussians which add together and give you the aggregate distribution for the entire population. So, the bottom histogram might suggest some kind of a mixture, that is the point here. Let us understand where this data is coming from, and I think that will make the context clear. There are entities called neutron stars, some of them are pulsars. Neutron stars are some of the densest objects in the universe. So, the density of a neutron star is something like 10 to the power 17 kilograms per meter cube, whereas Earth density is in a few thousands of kilograms per meter cube. That is the kind of density difference we are talking about. Neutron stars are primarily made up of neutrons, but there is a well known proportion of electrons, protons and neutrons here. You name a complication in physics, it is there, it is found in these systems. Some of these also emit in the radio, these are called pulsars, and it is a rotating star around some axis. Now, the magnetic poles of this star might be aligned in a different direction than the axis of rotation, and the radio emission that we observe on Earth comes from the magnetic poles. This is a very strong coherent radiation, which is why it is able to reach us from such far away places. What you observe is if the observer is in the path of this radiation, that is when, as long as the observer is in the path of this radiation, one sees a beep or a pulse, and there is no signal until the next pulse arrives. So, what you get is, depending on the rate of rotation of a neutron star, you get a pulse sequence which is very regular in its periodicity. This is not although it is a very dense object, it is not a rigid body in the sense of as an idealization in physics, it is not a rigid body. It has structure to it. Different regions of a neutron star have got different densities, different characteristics, different phases of matter, and so on and so forth. So, in neutron stars one sees a phenomenon which is somewhat similar to earthquakes on Earth, and these kinds of interactions between the crust and the core can lead to sudden speeding up or slowing down of the neutron star object, and this gives rise to what are called glitches. This is a rotating object, it has some energy, some of it is being dissipated in the form of radiation. So, in general this object is slowing down at some rate over astronomical time scales. What happens is, when there is a glitch, there is a glitching event. If we look at the period of rotation as a function of chronological time, then the period of rotation is increasing because of what I described. Whenever there is a glitch, suddenly it suddenly it speeds up, that is why the period decreases, and then again the slowing down starts at a different location on this vertical axis. So, this event is called a pulsar glitch. So, pulsar glitches could be are believed to be the result of quakes, star quakes, if you want to call it that way, which are basically related to interactions between the crust of the star and interior. It could also be related to shape changes and so on and so forth. So, the idea here is to find out whether these glitches come from the same physical mechanism, or there could be multiple mechanisms involved. So, these are the essential key questions that we would like to address. Are all the observed glitches caused by the same one universal mechanism? Could there be different glitching events related to different mechanisms? So, for example, some of the glitches could be related to a relatively higher up layer in the crust core interaction. Some of the higher energy glitches could be related to a deeper layer in the neutron star, maybe. And the question is, whatever data we have, do they have any indication that there could be multiple mechanisms, multiple physical mechanisms possible? Could there be multiple populations of glitches, implying at the physics end that there could be more than one different mechanisms that cause glitches? This is a standard way in which neutron stars are summarized. What you have in this plot is, each neutron star object, there are a few thousand which are observed so far, which are known to exist. So, on the x axis, what is plotted is the logarithm of the period of rotation, and on the y axis you have the surface magnetic field. These two are two fundamental physical entities that characterize a pulsar. These are intrinsic quantities, these are not related to the environment in which the star exists and so on. So, these have some kind of significance from the fundamental physics point of view. Okay. So, the pulse, the rotation period is something that is an observed quantity or a measured quantity based on observations, and the vertical axis represents the surface magnetic field. This is an inferred parameter based on some physical model that relates pulse period and the rate of change at which the spin rotation period changes. Okay. So, what you see from a statistics perspective is that there is some sort of a linear relationship between these two quantities, log of the magnetic field versus log of the period. So, in the log scale it looks linear. What you see here, you can see that there is some kind of a greater density of objects at this end. If you look at the values of the log of the period, this is in period is in seconds. So, what you see here is in the millisecond regime, these are what are called millisecond pulsars. This bunch is what are called normal pulsars, but again there are lot of subcategories of neutron stars that neutron star physicists talk about, and they are all mixed up here. One of the problems that people would like to address is looking at this kind of data. Can you figure out if there are separate groups of objects from purely by using statistical methods without taking recourse to the physics of the problem. So, the primary data which was summarized here in these histograms, the primary data is what is called a glitch magnitude. This is okay. Instead of describing the thing in terms of spin period, which has dimensions of time, people go to the frequency domain, and what you have here is delta nu is the change in the frequency across a glitch, that divided by the average frequency of rotation. So, this is what is called the glitch magnitude. So, it turns out that the glitch magnitudes are approximately in the range of okay, it is a relative quantity. So, it is dimensionless. So, the numbers are to the tune of they span several orders of magnitude from 10 to the power minus 11 to 10 to the power minus 4. Now, the key thing here is that observations in this regard are so precise that delta nu by nu values are extremely well determined. The error bars involved are really tiny compared to the magnitude of the glitch. So, one of the first concerns we talked about whether these horizontal ticks, how variable they are, how movable they are across data realizations, this concern is now eliminated. We can just assume that they are nearly fixed. The error bar is smaller than the width of the tick, for example. Other thing is the two histograms that were plotted were two fundamental physical quantities. So, for example, delta nu by nu, it can be shown that it is related to the change in the angular momentum of the neutron spinning object, and delta nu times nu is related to the rotational energy of the object. Now, so the point is, we are now going back to the original physics question of whether there are more than one possible mechanisms possible for that are responsible for the observed glitches. This translates to whether there are multiple populations of glitches in the data. So, we are essentially asking the question that is there any evidence either for or against the presence of multiple populations in this delta nu by nu or delta nu into nu data. Again, this is just the same data and histogram. One of the approaches that one can take here from a purely statistical perspective, without, although we talked about the physics context of this problem, we could take a purely statistical approach here, and given the question, one possible way to reduce it to a statistical formulation is to look for multimodal structure in the delta E, which is delta nu into nu, and delta nu by nu, which is related to the angular momentum. You look for signatures of or evidence for multimodality in these quantities. So, this can be formulated in the standard way as a hypothesis test problem. I will not go into details of what hypothesis testing is, but we will just assume that you have really basic notions about this thing. So, here the null hypothesis, as it is called, that is the prevailing state of understanding. So, H 0 stands for the null hypothesis, which represents your current state of understanding. Let us say that the null hypothesis states that the distribution is unimodal. We have no reason to expect that there are more than one mechanisms. Against the alternate hypothesis, typically denoted by H 1, this is it says that the distribution is not unimodal, it is multimodal. Okay. So, this is the question that we are exploring. We want to get some feel for that. So, we start with assuming that there is no reason to expect that there are more than one mechanisms, versus the alternate picture, alternate theory, alternate explanation is that you have your observed data says that or your observed data is explained better by assuming that there are more than one mechanisms. So, this cutting short the long story in between, there are several statistical tests which are well established, whose formal properties are well established. These are the tests listed here. These are some of the tests for checking for multimodality of distribution. So, there is something called a dip test, which looks for dip in the distribution. There is something called Silverman test. Again, this looks for multiple modes, and there is a test which tests for single mode, single peak versus two peaks. That is called the bimodality test. The result of these tests, results of these tests are summarized in terms of what are called the p values. There is large body of literature about p values and how they are used and oftentimes misused. Okay. The way a p value is interpreted is that the p value is a measure of the evidence against the null hypothesis, and specifically lower the p value, greater the evidence against the null hypothesis. That is how one interprets it. So, in this case, smaller the value of p corresponding to a test, that means that the evidence is greater against the hypothesis of unimodality in the context of these tests. So, in the table here what you see is these three tests are applied to the two separate quantities, delta nu by nu and delta nu into nu, and what is listed here are the p values, computed p values. These are quite small, the only fairly large one is here. It looks like these tests, all three tests, especially with the delta nu by nu data, all three tests are suggesting that the data is not in favor of the null hypothesis of unimodality. Now, this p value, it is about 10-15% on the probability scale. This is a fairly large number as far as significance testing, as it is called, is concerned. But then this is clearly, if you recall, it is about this quantity. If you look at this histogram apart from this vertical bar is not suggesting multimodality, it is more like a broad peak. So, presumably this somewhat large p value is a result of that. The other piece of caution I would like to, or a disclaimer here is, using multiple tests to test for the same thing can lead to statistical issues. Now, here we are doing this exercise only at an exploratory level. So, that is the only sort of weak justification for what we have done, and the whole thing is that these tests are suggesting that the data may be multimodal rather than unimodal. Another piece of result which is slightly more technical is this Silverman test allows you to test for one mode against two modes, 2 against 3, 3 against 4 and so on and so forth. So, the null hypothesis for the Silverman test could be any number of modes, and it tests for, if your null hypothesis hypothesizes k peaks or k modes in the distribution, then the alternate hypothesis is k plus 1 peaks. So, a Silverman test allows you to test for such different number of peaks in the null hypothesis. So, if you compute the p value as a function of the number of modes or number of peaks in the null hypothesis, you get these kinds of plots. So, 1 against 2 is where the p value is really small, but 2 against 3, 3 against 4, 4 against 5, these p values are fairly large. So, you can't really say about anything about whether there could be anything about the number of peaks that way. It just says that the data is more consistent with more than one peaks. Similar thing is obtained with the delta E data. The same Silverman test says that when you have null hypothesis of one peak, one mode against 2, you see that the p value here is very small, but the p values for all other number of modes in the null hypothesis are fairly large. So, you can't really rule out 3 in favor of 2 or some such things. So, both these results are consistent with multimodality rather than unimodality. Okay, let us continue with the second part of the previous session. This is about multiple populations in pulsar glitches. This continuation from part 1. So, we started off with this these two data sets. We looked at how the problem could be formulated in terms of standard hypothesis testing formalism. We looked at some of these results, which all of them, almost all of them except this one, are suggesting more than one modes in the glitch magnitude distribution and energy distribution. Here is another take on the same problem. So, even if there are multiple glitch populations, the resulting distribution need not necessarily be multimodal, and it could, for example, be a broad single peaked, but somewhat broadly peaked distribution, which could again be the result of multiple distributions underneath it. So, the second approach we try, the second formulation that we try is to assume that each glitch population is a Gaussian distribution, has a Gaussian shape for in both delta E and delta nu, and then the statistical formulation that arises from this thing is to model both delta E and delta nu by nu as Gaussian mixtures. Gaussian mixture models are, we will talk about them in a minute. Then the question is to figure out how many Gaussians in the mixture account for the data best. The caveat here is that this assumption of Gaussianity for each glitching population is probably not justified. I am not sure about that, but this is just done in the spirit of exploration. What one expects for the individual glitch population, even if there are multiple mechanisms, what does one expect for that? It is not clear. We have just assumed that it is Gaussian, but this assumption is quite ad hoc. But nevertheless, whatever we get out of this approach might shed some light on the underlying, the original problem of multiple mechanisms, and hence we just try it as an ad hoc approach. Okay, Gaussian mixture models are models in which the probability density function for the data, x represents the data variables, f represents the probability density function. These are the parameters of the distribution. The probability density function underlying the data x is considered to be a mixture of individual Gaussian densities. X again represents data, and this mu k and sigma k are the mean and standard deviation parameters, and this pi is called the weight or the probability of each individual Gaussian. and you have this summation here. You are summing over different Gaussian components, basically you are adding them together at the data values. So models of this form are called mixture models, and in particular if your densities that go in the mixture are Gaussian, these models are called Gaussian mixtures. The Gaussian density has this standard form. The question is, now given a mixture, suppose you say that you have a Gaussian mixture with some 2 components or 3 components, 4 components, you name a number, that is this k, total number of components is this k. You want to estimate these parameters, which are the mean and standard deviation of the Gaussian and the weight of each Gaussian in the mixture. So, these are the unknown parameters which are to be estimated from the data, which is your the x here represents the data variables. How is this done? One way in which this is done is to write what is called the likelihood function, which is considered a function of the parameters and also the mixture size. It also depends on the data. This is basically product of the density function here, density function of the Gaussian mixture model. This is this f, product of the density values at the data points given values of the parameters. Now, of course, we do not know the values of the parameters, we can write down this expression analytically as a product, and making estimates of the parameter values for a fixed k. This is done by maximizing the likelihood function. So, this is basically saying that you choose values of the parameter that maximize this product. Now, this product has the interpretation, if these data points are independent, this product represents the joint multivariate density of your data, and whatever you observe, which is the observed data, cannot be a low probability event. Hence, you choose your parameters of your model, statistical data model. In this case, they happen to be the vector of weights, means and standard deviations. You choose your parameters, choose the parameters of your model in such a way that this joint probability density function for the observed data is at its maximum. So, this method is known as the maximum likelihood method. In the context of Gaussian mixtures, there is a celebrated algorithm called the expectation maximization or EM algorithm. This maximizes the likelihood function in a numerical way. It is an iterative algorithm consisting of 2 steps, and the algorithm keeps on alternating between the E step and the M step. Here are the expressions for computations that happen at each step, never mind the details of it, but basically you keep on computing this quantity and then use this quantity in the M step, then the quantities computed in the M step are used back in the E step, and so on and so forth, and you keep on doing this until the vector of your parameters does not change appreciably across iterations. This is typically how iterative numerical methods work, and EM algorithm also works in the same fashion. So, basically at a fundamental level, you are estimating parameters by maximizing the likelihood function, which we talked about, and now the form of the likelihood function turns out to be analytically intractable. You can't just find the derivative and set it to 0. This is where one has to resort to computation and specifically a numerical method called the EM algorithm, and iterate the EM algorithm until you have numerical convergence. That is how it works. For a fixed number of components k, this is the algorithm that will give you estimates of the parameters as maximum likelihood values. The other question still remains unanswered. How do we choose this number of components? Now, this number of components in the mixture define the mixture model that you are using. You know, for each different value of k, you have a different model, different statistical model here for the data, right. So, this takes us into a class of methods, class of statistical methods, which are called model selection methods. One of the model selection methods is based on what is called the Bayesian information criterion. The form of this Bayesian information criterion, which is a function of the mixture size k. this is twice minus 2 times the log of the likelihood function at the maximum likelihood point, plus something that depends on the number of parameters and also the data size. So, the number of independent parameters in the Gaussian mixture are 3k minus 3, because for each model size k there are 3 parameters, 2 parameters from the Gaussian density and 1 is the weight, and because one of the weight components is not independent, because if you specify okay, it has to be 3 times k minus 1 rather than minus 3 in this case. One of the weight parameters is not independent because all these weights pi have to add up to a 1. So, because of that one constraint you have a minus 1 here, this is a mistake here. So, this BIC has this form. It is an interplay between the likelihood which measures the conformity of the fit with the data, and this quantity basically is a penalty on the number of parameters. So, for sufficiently large k this will start dominating, for sufficiently small k it is this likelihood part which dominates, and there is a as a function of mixture size there is an interplay between the two, and there is a minimum in between somewhere. So, that is the value. So, the value of k, which is the size of the mixture, you choose it so that this BIC is minimum. That is the prescription for model selection using the Bayesian information criterion. That is what we use. Going to the results, this is what we get. The black ticks are the data. For reference, I have also included the histogram as the gray bars, and what you see here, the two colored curves red and green are the fitted Gaussians, and together when you add them up together you get this black curve which is the estimated mixture density with 2 components. This is with 3 components. So, you can see that with 3 components between 2 components and 3 components there is obviously a change in the estimated mixture density. So, there is a little shoulder here which is not present here, that is clearly a result of this green component here, and this peak is presumably better modeled by this blue curve here, blue Gaussian here. You could similarly analyze the bottom 2 plots. This is for the delta nu by nu, the top row, bottom row is for the delta nu into nu or delta E. What you see on the right hand side column is BIC as a function of number of model components. What is actually plotted is what it is denoted by delta BIC, which is BIC for given number of components minus the minimum value of BIC across all the components, right. We have looked at up to 5 components from 1 to 5. Clearly 2 here is where BIC is at its minimum, but then 3 the value of BIC at 3 components is also sort of close here, not too far away. So, maybe there are 2 components, 2 Gaussian components in the data, 2 Gaussian components explain the data well, maybe 3 Gaussian components explain the data well. You get similar results for delta E data also. Again, between 2 and 3 there is probably not too much difference. Across data realizations you might be able to see both these components, which is why 2 and 3 are sort of close in terms of their BIC scores. So, another way of looking at the same model selection plot is to turn these, there is a way in which you can turn these delta BIC values into probability of the model itself. These are technically what are called model selection probabilities. I will not go into details of that, but these probabilities again turn out to be okay, the highest probability is realized at 2, 3 is a bit somewhat lower, and 4 and 5 are quite low, for 1 is the lowest. Again you see a similar picture here in delta E. Model selection probabilities for 2 and 3 are sort of close, not exactly close, but sort of close, but 1, 4 and 5 are quite close to 0. So, this is again an indication that one Gaussian component is certainly not a viable model for the data for both the quantities, and 2 seems to be the most likely possibility, maybe 3 is also a possibility. So, going back to the original question of one population versus more than one population, one physical mechanism for glitches versus more than one mechanisms, both the statistical approaches tried. The first one was hypothesis testing, the other one was based on Gaussian mixtures. Both these approaches seem to suggest that one is not a viable candidate to explain the data best. It is more like 2 or possibly 3. I think over the years, getting greater data, observing a lot more number of glitches will help resolve this issue over the years. But even at the current level of current size of the data, current number of glitches observed, it does suggest that there could be more than one possible physical mechanisms which are involved in the glitching events, and this is certainly an important input for neutron star theorists from a fundamental physics point of view. Let us move on to this session. This is a third case study as part of these talks. So, this is about a branch of statistics called non-parametric statistics, non-parametric inference as applied to the astrophysical phenomenon called cosmic microwave background. Okay, so, the context is that of cosmology. Here is a here is a data set. We will explain what these quantities are. It looks something like this thing, and this is power spectrum data from a the cosmic microwave background probe called WMAP from back from early 2000s, and we will see what this data is. And the idea is to, given this data, we want to estimate the shape of the underlying true power spectrum, and then there are many physics questions, many cosmology questions that are waiting to be answered from this. Okay. So, the key question is, the approach here is you can certainly assume the prevailing cosmology formulation and knowledge, and based on using that knowledge you can arrive at a fit using theories of physics and cosmology, but then without taking recourse to cosmology or physics, can you purely based on the data, can you figure out the shape of the underlying power spectrum? Another question is, there are competing cosmological models. So, can we rule out one in favor of another? We will refine these questions later on and give a background on these things. And looking at the data, it looks like there is a peak here. Now, of course, cosmologists also expect a peak here, another peak here, and so on. Can we find uncertainties on the peak location and peak heights? This is a more restricted question. We will see why it is important. This is some sort of a timeline for the universe. Universe began in the Big Bang right here. This axis represents the spatial extent, this axis represents the time. This is a schematic picture. Initially, the universe began as a very hot and very dense object. So, everything was bouncing off everything else, and for a very long time, until the temperature dropped sufficiently to sufficiently low values, nothing could exist in the sense of atoms or okay. So, about 380,000 years after the Big Bang, that is represented by this line, this is when the temperature of the universe fell sufficiently low so that first atoms could be formed. This is when initially the photons and the matter particles were interacting so heavily with each other that atoms could not form, and it was a really hot boiling soup of these things. This is where atoms started forming, and this is the point in time when the interaction between radiation represented by photons and matter stopped, and this is the point in time in the history of the universe when these photons started flying through the universe freely, and we observe them at, this is the present. At this point in time, we observe them in the microwave regime. Because of the expansion of the universe, these photons are getting towards lower and lower energies. So, we observe them at in the microwave frequencies, and as radiation can be characterized in terms of its temperature, this radiation at the current time is around 3 Kelvin. So, it is typically called the 3 Kelvin radiation or 2.7 Kelvin radiation. We will refer to it as CMB radiation. Cosmic microwave background radiation was discovered in the early on in the mid or late 60s, and Penzias and Wilson got a Nobel for that. From there on, the progress has been that around in the early 90s, people started sending out probes in the sky to measure the CMB radiation reaching us from different directions in the sky. And so, the early probe was called COBE, Cosmic Background Explorer. There are also many ground based experiments to measure the CMB. In the early 2000, this satellite probe called Wilkinson Microwave Anisotropy Probe was fired in space, and it kept on measuring CMB radiation from different directions, and it kept on spitting out data realizations every 2 years since then. What is measured by WMAP and a later probe which was sent around to after 2010, it is called Planck. So, what these satellite probes do is to basically measure the temperature of the radiation coming from different directions. The way sky is modeled is as if we are sitting inside a huge sphere and the surface of the sphere is at infinity. So, you are looking at a ball from inside, and different directions as measured from the center of the earth represent different points on the sphere. So, the locations on the sphere are characterized in terms of two angles, let us call them theta and phi. So, you have this temperature field as a function of different angular directions characterized by two angles. So, what is done is, okay, now the actual the way the data is collected and processed, it involves a lot more than what I am describing here. For example, the satellite keeps on recording radiation temperature from in different directions with a choreographed sequence which gives rise to what is called time ordered data. This time ordered data looking at the direction at which the satellite was watching for radiation, this has to be mapped onto the angular coordinates theta and phi. Now, this radiation is not free from contamination from variety of things. So, for example, in the galactic plane, because of the dust in the galactic plane, you get this band again in the microwave region, and this somehow has to be removed before the true cosmic microwave background radiation data can be obtained. So, this is one with the foreground radiation, and this is after removing the foreground radiation, and this thing is converted into the power spectrum data. This is the story in nutshell. In between, of course, you have the temperature field which is measured, which is this thing represented by this map. You take out the average temperature and scale it by the average temperature. So, this is some sort of relative temperature fluctuation as a function of angular directions. Anything related to sphere is oftentimes modeled using a mathematical device called spherical harmonics, and in terms of spherical harmonics, what you do is to define the power spectrum, which is a function of a coordinate called the multipole index, which is related to one of these angles. The term power spectrum, those of you who are familiar with Fourier transforms, is used in the similar sense, that when you talk about the power spectrum of a signal, you talk about the magnitude as a function of frequency. Frequency is the conjugate coordinate to time. In the same sense, this multipole index L is related to one of these angular coordinates, and this power spectrum as a function of multipole index provides some sort of a convenient summary of the CMB temperature fluctuations. On the practical side, this is in principle how it is estimated. These are matters of detail, and there is a fairly complicated data reduction pipeline that goes into getting this estimated CL data, which is the plot that we saw earlier, which looked something like this. How does one interpret the CMB power spectrum? The horizontal axis is the multipole index, vertical axis is the value of the power spectrum. Lower values of the multipole correspond to wider angular scales. So, if you threw out data from higher multipoles, the image might look blurry like this thing. At intermediate values of the multipole index, you see at a smaller angular scale. If you go to higher multipole values, it is even smaller angular scales. So, as the multipole index increases, your angular resolution goes up, and we expect peaks in the angular power spectrum. This is the typical shape that we expect for the angular power spectrum based on physics and previous data. Okay, why is the cosmic microwave background itself considered so important? Because first of all, it was one of the key predictions of the Big Bang model of the universe, and observation of the cosmic microwave background firmly established the Big Bang model as opposed to alternate models which were prevalent earlier. It established the CMB model firmly, I mean the Big Bang model of cosmology firmly against other models. CMB, as we saw, is a relic from 380,000 years after the Big Bang. On cosmological timescales, this is a minuscule amount. So, cosmic microwave background radiation is some sort of a relic from a very early universe, and it contains frozen signatures of specifically of density fluctuations in the early hot soup which was the universe. There are competing models even within the Big Bang umbrella of models, and hopefully the CMB data will tell us something about which model is better supported by data, which is not, and so on and so forth. More specifically, all these models, cosmological models, come with their own set of cosmological parameters. Cosmological parameters, for example, are the total mass of the universe, total energy content of the universe, so on and so forth. And the CMB power spectrum specifically is related to these fundamental attributes of the universe in a very sensitive fashion. So, for example, height of the first peak is related to the total mass content, height of the second peak is related to the total baryonic mass, height of the third peak is related to what is called dark matter, and so on and so forth. So, estimating the CMB power spectrum well, getting uncertainties on the peak locations and peak heights has a direct bearing on what we can say about the cosmological parameters. It allows you to estimate the cosmological parameters in an direct or indirect fashion. As was advertised, we are using a non-parametric methodology here for this purpose. A non-parametric statistics relies on fewer number of assumptions about the data. Specifically, since we are talking about estimating the underlying regression function in this context, non-parametric regression, I would like to say that non-parametric regression relies on less number of assumptions about the data. For example, if you say that your data underlying dependence of y on x is linear, you are already saying that your underlying model is linear and the parameters of the model, which are the slope and the intercept, are to be estimated from the data, whereas non-parametric methods will try to avoid making these kinds of assumptions about whether the data is linear or quadratic or quartic or so on and so forth. Is it polynomial, is it exponential? These kinds of in the statistical jargon, these are called models of the data. Non-parametric methods will avoid doing these assumptions. Non-parametric methods do make assumptions, but these are weaker assumptions. Non-parametric methods work better with larger data. CMB data is a good candidate for that. Non-parametric methods allow estimating the optimal smoothing from the data itself, which means it allows you to estimate the regression function in an optimal fashion from the data itself. Here is a technical point. The particular method that we are going to talk about later on also gives you uncertainty in the estimate in terms of what is called a confidence set, and this confidence set is a powerful construct of this particular method. It allows you to ask all kinds of interesting physics questions and get answers for those based on the data. One of the things that this confidence set allows you to do is to take a parametric fit coming from a cosmological model, for example, and see how close it is to the non-parametric fit, and if it is too far, then there is a good chance that this particular fit is not a viable candidate for the unknown truth. That's how a statistician would look at it. The particular method we use is model independent in the long run. It does not depend on the it does not make it makes almost no assumptions about the particular model for the data. Let us talk about this notion of optimal smoothing. This is again related to bias variance trade-off that I had mentioned earlier in one of the sessions. Here are two data realizations. The rows correspond to two data realizations, and the columns correspond to three different levels of smoothing. If you are at the rightmost end, this is specifically the prescription is that no matter which value of x, you simply take the average of all the y values and take that as your estimate for the regression function. Now the problem here is across data realizations, this particular fit does not change all that much, but then you can clearly see that this fit is quite far off from the data, and the data is clearly suggesting some sort of an increasing function of y as a function of x. So, this is across data realizations you expect less variability, but the fit is quite far away from the underlying dependence of y on x. So, we say that the bias is high, but the variability is low. At the other end, let us take the prescription that you simply join the successive points with a straight line. So, what you get are fits which are extremely wiggly obviously, and the fits will clearly vary extremely across data realizations. But then this prescription tends to capture the increasing dependence far better than what is captured here, right. So, we say that at this end the bias is lower, but the variance is much higher. So, what we need is not these two extremes, but somewhere in between, where the fit that you obtain with some prescription is kind of, it picks up the trend in the data, but it is neither too variable nor too biased. So, this is the operating principle behind non-parametric regression methods, and that relies on the notion of optimal smoothing. So, this fit is some sort of an optimally smoothed version of the data. That is how one can look at it. This bias variance trade-off also shows up in the plotting of histograms. We have talked about it couple of times earlier. Here is an actual illustration, visual illustration. At this end, the bias is high, but the variability is low because the number of bins is a bit too small. At this end, the bias is low, but the variance is high. Across two data realizations, the visual look of the histogram changes drastically, but then the whichever histogram you look at, it is presumably capturing the density variation in the data much better than at this end. This is somewhere in between. This is close to the optimal binning, and in this case the bin size or the number of bins is the parameter across which you find the optimal smoothing, and we want to avoid both these ends. We want to have a histogram chosen somewhere around this number of bins for this particular data, and again you see the phenomenon of bias variance trade-off here also. To paraphrase, to summarize this bias variance trade-off in a schematic fashion, There is some kind of a smoothing parameter. In the histogram example, it was the number of bins or the bin size. In the regression example, it was the number of parameters you use to fit the the number of parameters, for example, to characterize the regression function in some sense. So the larger the farther away on this axis is greater complexity or less smoothing. At this end you have got higher bias, which means smoother fits. At this end you have got more wiggly fits, greater bias, less variance. And if you add these two together, then you have a behavior. This quantity is oftentimes called risk of the fit, and you see a minimum somewhere, and this is what gives you the optimal smoothing. So, this is a schematic way of representing this bias variance trade off. This is the second part of the previous session about non-parametric inference for the cosmic microwave background. We are continuing from part 1 of this thing. We talked about bias variance trade off and optimal smoothing. So, this particular methodology that we use, it is called REACT. There are references at the bottom of this thing. So, this is a regression methodology based on what are called orthogonal functions, and optimal smoothing in this case is obtained through a process called shrinkage. We will not go into details of that, it is a fairly technical thing. So, when we apply this thing to the WMAP data that we saw earlier, this was the WMAP data, cosmic microwave background power spectrum data coming from the WMAP probe after first year of its operation. So, it is called WMAP 1. So, this is the power spectrum axis, this is the multipole axis as we called it. The green points are the data points. Let us take a little closer look at the data scatter. The characteristic of this particular data set, and you will see that this is also the same for other data sets in the WMAP series, is that the vertical spread is much lower at this end. It actually is supposed to go a little bit up at this end. The vertical scatter is a little higher here compared to this part here, and as you go to higher multipoles, this essentially grows very fast. So, the variability on at higher multipoles is generally on the higher side. It is also a little higher around the peaks power spectrum. It is also supposed to be higher at the towards the lower end of the multipole index. This is at this end, it is related to what is called a cosmic variance, and at this end it is related to less coverage at those angular scales. The other characteristic that I did not mention earlier is, when you, as I mentioned, this satellite probe is measuring CMB radiation coming from all directions in the sky, and you need to take the part of the radiation which is coming from the galactic plane. You need to take it out from the data. Once you do that, it induces correlations in the data, and those correlations reflect in the CMB power spectrum also. So, you have got two statistical characteristics in this data. One is that of variability which changes with multipole. This phenomenon is called non-constant variance in the statistical literature, or there is a complicated word for it, it is called heteroscedasticity. So, these data are heteroscedastic, that is one characteristic, which means variance changes from one value of the horizontal coordinate to another. And secondly, there are also correlations across the data points. So, you change one data point, it reflects somewhere else, and so on and so forth. So, your methodology has to take into account these features of the data. The particular methodology which is explained in these papers does take care of heteroscedasticity, and also the fact that these data are correlated, and the correlation matrix or the covariance matrix is available from some other source, which is what we use in obtaining the fit. The fit is obtained through mathematical devices called orthogonal functions, and optimal smoothing is obtained through a process called shrinkage. This is roughly the description of the method. This particular black line is the react fit for the first year WMAP data. What you see is that the first peak here is quite well determined, and it's not at all a surprise, because even if you ignore this black line, this data itself is showing a peak here, and given the variability, given the less amount of variability in this region up to about here, it is very easy to see that this peak is quite well determined, and the method is picking that up quite well. Another peak is expected around this region, and a third peak is expected around here. Now, looking at the variability here in this around here, the peak is quite shallow. It looks shallow also because of the vertical scale. Okay, in principle the data values can, the power spectrum values cannot be negative, but the values are negative. That is a for the data, that's because of variety of artifacts in the data. So that is not, it's not something to be concerned about. The method basically takes care of this thing. Okay, so the second peak is not really visible. So you might be able to see visually a tiny, rather shallow peak around here, but whether this peak is real or not, this question can only be answered by looking at the variability in the peak position and the peak height. If it is too much, then there is no point in saying that the peak is really there. Now, cosmological models, when you use model based fits, they do find a peak here, they do I am talking about the situation back in around 2001, where cosmological models predicted these peaks, and these peaks were seen in the fit because the fit was based on these models. So, from a purely model independent point of view, if I say that I am not going to assume any cosmological knowledge, I am not going to assume any physics, I am purely going to look at the data and ask the question whether I see a peak here around or not, then just based on the data scatter you would be a little skeptical about this second peak, right, because the variability is too large. So, the essential point is any statistical method that tries to address this kind of a question has to give a prescription for finding uncertainties on answering the question of how uncertain is this peak in terms of its vertical variation as well as the horizontal variation. Now, the same applies to the peak which is expected in this region, and the problem is even compounded, is even more complex because the variability is extremely high in the data at this end. This variability can be reduced by adding more data to it, which is essentially what happened with the further releases of the WMAP data. We will see that a little later. Before that, let us try to understand how these uncertainties are computed in this method. So, we need to understand the confidence set construct. Okay, this is some sort of a picture of this space in which the power spectral fits sit. The center of this particular confidence set, which is by construction a spherical or an ellipsoidal set, the center of it is the non-parametric fit that we obtained. Let us call it the react fit. The truth, unknown truth, might be somewhere here. This is just a schematic way of looking at it. The confidence set is computed at what statisticians call levels of confidence. What that means is, if you look at this particular contour which is marked as 67%, this is a schematic picture, do not interpret it literally. What this means is, by interpretation of the confidence set, the probability of finding the unknown truth inside this particular circle is 67%. If you want your inferences to be at a higher level of confidence, the size of this set necessarily expands. So, at 95% confidence, you want a confidence set which contains the unknown truth with 95% probability or 95% confidence. You need to go to a higher, a bigger confidence set. This is typically how confidence sets behave. Larger the confidence, the size of the confidence set has to be bigger. If you want 100% confidence, the entire space of these power spectral fits will have to be included there. This is just saying that at 100% confidence, you are just saying that the unknown truth is somewhere inside this space. So, that is not really giving any information at all. So, people typically work at 67 or 95% confidence. Now, the point is, each point in this space, the center of the confidence set is the react fit. Each point in this space represents one power spectrum, which is considered a candidate for the unknown but true power spectrum which underlies the data. This confidence set feature is confidence set construct which comes with this particular methodology gives a powerful way of finding uncertainties. So, for example, if you want to find how much variability one can expect in the first peak which was well determined, say at 67%, what you do is basically somehow move around this in this 67% confidence set, record the height of the first peak at each point in this confidence set. As I said, each point in this confidence set now is one power spectral variation. So, record where the first peak occurred, record its location, record its height, and at the end of this exercise, by traversing this confidence set, in principle every point, you have a whole collection of values for the location of the peak and height of the peak. You take the minimum and maximum of these two, and that gives you the range of uncertainty, the range for the uncertainty basically. When I say that this is a 67% confidence set, what this means is the probability of finding the unknown truth inside is 67%. There is still a chance that the true but unknown spectrum underlying the data, underlying our universe, is somewhere outside of this confidence set. Hence, people would like to go to larger confidence, which says that at 95% your inferences have a chance of being wrong with 5% probability. That is basically what it means. Okay, so, this is in a nutshell the prescription by which uncertainties on features of the power spectrum can be found out in this particular method. This is the WMAP first year data and together with its react fit. Okay, we'll come to uncertainties later on. When you go from first year WMAP data to third year WMAP data, first of all the uncertainties are reduced, and secondly the range of the multipole indices, range of the angular scales is increased. You are looking at finer angular scales compared to the first year WMAP data. Fifth year WMAP data, the smallest angular scale remained fixed, but then the uncertainty on the data got reduced. This is where the second peak started getting better resolved because of the reduction in the vertical scatter here. It became even better here. Now, the uncertainty on the third peak is getting reduced with reducing vertical scatter. At the 7th year level, you see a peak here, but the vertical uncertainty is quite high in this region. The range of multipole indices got extended here quite a bit. So, you are going to much finer angular scales here. For this particular work, we stopped at the 7th year WMAP. There was one or maybe one more release of WMAP data later on. Okay, going back to uncertainties, if you take the first year WMAP data, this is the picture that one gets. These are uncertainties both on peaks and the dips in the power spectrum. So, the first peak, as we said, as we saw from the data itself, was pretty well determined, and each of these points in this scatter represents one peak location, peak height in one of the variations that one visits inside the confidence set. We worked at the 95% level of confidence or probability that the true but unknown power spectrum is inside the set with 95% probability. Each color represents one peak or a dip, and each point here, for example, this point represents one power spectral variation in which the peak height was this thing and the peak location was this thing, slightly less than around 200 maybe. So, these scatters give you an idea about how the peak locations, peak and dip locations and heights are distributed inside the confidence set at a particular level of confidence. The first peak is very well determined, second peak not so much well determined, third peak not so much well determined at the first year WMAP data, and especially on the last peak the uncertainty is very high. So, at the if you do not assume any cosmology or the physics of this phenomenon, then you would not be tempted to conclude that there is necessarily a peak here or a dip here and so on. But situation gets better with further releases. The first peak, first dip, second peak get fairly well determined, well resolved. Uncertainty is reduced because of better data quality. Going from third year to fifth year, things get even better. From fifth to seventh, things get even better, but of course, the uncertainty is much larger at the rightmost end on the multipole index, or at the finest possible angular scales, the uncertainty is still much higher. As far as one of the questions that we posed is how well determined are the peaks, just purely based on data considerations, what can you say about how well determined are the peaks? Now, across realizations of the WMAP data, we saw that peaks are slowly getting resolved better and better. The other question is, other kind of question one can ask and get answered through this method is, suppose you have got even within the Big Bang umbrella of models, you have got several competing models. What can you say about the model based fits and how close are they likely to be to the non-parametric fit? And extending the logic of the confidence set, the formal guarantee says that if you are working at 67%, then the formal guarantee says that the probability of finding the unknown truth inside the confidence set is 67%, or working at 95%, the probability of finding the unknown truth, which is the true power spectrum, which we assume we do not know, is 95%. There is a chance of 5% that it can still be outside, but then this method, this confidence set construct essentially says that every point inside this 95% confidence set is a potential candidate for the unknown truth. Now, this is an interesting statement, because what this says is, this is the react fit which by construction sits at the center of the confidence set. You take a parametric fit coming from a particular cosmological model and put it inside this space and see where it is. If you are working at the 95% level, and if you find it somewhere here, let us say this is the parametric fit, although I have labeled it truth here, take any point, it does not matter. Suppose your parametric fit coming from a cosmological model called say lambda CDM model is here. What this means is, at the 95% level, you cannot rule out this point as a potential candidate for the truth. It is in the game. But if it was sitting somewhere here, for example, at the 95% level, you would have said with 95% confidence that this is unlikely to be, not likely to be a candidate for the unknown truth. So, you can make these kind of statements using this method. Of course, cosmologists will say that we know the physics pretty well, we do not need this kind of insight, but nevertheless this method provides an independent corroboration of the cosmological knowledge. That is the point here. Okay, so, we did this interesting experiment here, where we took the standard lambda CDM model and compared it with the power spectral fits coming from a variant of the lambda CDM model, which has a small fraction of neutrinos in it. So, such models are called hot lambda CDM models. What we do is obtain the parametric fit from lambda CDM model, obtain the the parametric fit from the hot lambda CDM model, and we of course have the non-parametric fit and the confidence set for each of these WMAP realizations, and then we have the associated confidence sets for each of the WMAP data realizations. Let us simply look at the distance of each of these parametric fits from the non-parametric fit, which is the center of the confidence set. What you see is that if you now traverse vertically each column, you see that across data realizations 1 year, 3 year, 5 year and 7 year, the distance of the lambda CDM fit from the center, which is the non-parametric fit, goes on reducing, whereas if you put a small fraction of neutrinos, the distance keeps on increasing. And this essentially, I have not mentioned what confidence level this distance corresponds to. That depends both on the model and on the data realization, confidence set corresponding to that data realization. But this these numbers do not necessarily mean much. You really have to look at the confidence level at which corresponding to each of these distances. Now, with the hot lambda CDM model, this you need to go to a really very high level of confidence for this to be a viable candidate for the true power spectrum. So, essentially what this means is this model is essentially ruled out as a candidate for the unknown truth. So, this is one of the nice things about this method. This is also one of the powers that this method has, and which allows you to answer complicated physics questions purely based on data considerations. Because in arriving at this table and corresponding results, we have not relied on any physics assumptions, that is the point, and yet the known physics which points at the lambda CDM model is corroborated in a very nice fashion without resorting to any physics assumptions. Here is another feature of the physics of the early universe, which comes out very nicely from this methodology. What is plotted here is the correlation between peaks, which means you look at how the first peak and the second peak vary. So, this is the location of the peak in the multipole index. So, L1 is the location of the first peak, L2 is the location of the second peak, and this is the scatter as seen from the confidence set for the location the joint location of the first and second peak in the L1 L2 plane. And you see this kind of scatter again. Okay, the first peak, okay, this is okay, I do not remember which data realization this is for, but the first peak being extremely well determined and a second peak also, this is probably at the 7 year level, 5th or 7th year data. You have a very localized kind of scatter here. What is important here is these peaks are known to be harmonic peaks, in the sense they arise out of acoustic oscillations of the early universe, and hence here we expect some sort of a lattice structure here, and looking at the scatter across the in the confidence set, you look at the pair of peaks and look at their locations and how they vary across in the confidence set. This is the kind of scatter one gets, and this scatter is clearly showing that arbitrary possibilities for the pair of peaks is not possible, and and in particular this scatter suggests a regular lattice kind of structure, and this is corroborating the harmonic physics of the acoustic oscillations of the early universe. And later on we applied the same method to the Planck data. Planck was the satellite from the European Space Agency, which was fired in around 2010, and this is the non-parametric fit for the Planck data release from 2013, and you will see that eventually things got much better, and uncertainties on peaks and dips really got very well resolved even from a non-parametric point of view, and that helped. I mean, this is an independent model, independent verification of the known physics of the Big Bang essentially. To summarize, what we did here is we saw how the known, in this case the known physics, how it is elicited from data in a model independent purely data driven approach. The non-parametric inference method that we used gives a provides a powerful approach which is complementary to the mainstream model based approach, statistical approaches, and in this particular case the model based in this particular case the known physics was corroborated without assuming it, which is the nice thing that came out of this exercise. So, that is all for now. Okay, in this last session, let us take a broad overview of what we went through. Okay, specifically what we did was in the initial sessions, we went through a really quick and essentially a dirty introduction to a statistical computing environment called R. I am just hoping that whatever we did was just enough to give you a head start into learning R on your own or with the help of experts or resources. And then later on we delved into three case studies. These are case studies in astrostatistics, and these case studies hopefully illustrated how a scientific question gets transformed into a statistical formulation or one or more statistical formulations, and how it helps extracting useful information from the data, which can in turn help the scientists, physicists and cosmologists in this case to revise their theories and observations. Okay. So, one of the things which I hope has come out of this exercise is, first of all, the three case studies that were presented are examples of data driven science. So, there is a science context to it, there is a scientific question which is to be answered or solved. An answer is sought for some question based on there is some data which is available, and this data is relevant for the question. The data is assumed to contain information which is relevant to answering the scientific question which is being asked, and then this pair of things together lead to a statistical methodology, lead to formulating the problem in a statistical fashion, and then that decides which statistical methodology is to be used, and it leads to either an answer or some progress at least. So, this is some sort of a characteristic of what I might call data intensive or data driven science. Now, even if we say that we are using statistics and computing heavily, we are doing data intensive science, data driven science, what is important to realize is there is the problem necessarily comes from some problem domain. In this particular case, all these case studies came from astronomy and astrophysics. The relationship between astronomy and astrophysics, to put it in a nutshell, astronomy is the observational part, and astrophysics or the physics behind it gives an explanation for what we observe. So, the problem comes from some domain, and you cannot really ignore the domain aspects of the problem, because oftentimes the domain aspects are firstly they need to be understood in order to understand the data, and the domain aspects oftentimes provide you with clues about which methods might work better, which methods should not be used, and so on and so forth. The methodology domain that we talk about is primarily probability and statistics, or statistical inference, if I may put it that way, and this is primarily because we are dealing with data, and the data have got uncertainties in it. We can't exactly gather data which is infinitely precise. If we had infinitely precise data, we would not have bothered to invent probability and statistics in the first place. So, the methodological domain is statistical inference, because the data have got uncertainties in it, and then essentially you need to reason out about the problem domain based on uncertain data. So, this is reasoning under uncertainty, if one can put it that way. And at the practical level, all this thing oftentimes boils down to the technological domain of computing. I mean, I am making rather broad and broad categories here. Computing, okay, some people will disagree that computing is purely technological. There is a strong formal base to it, anchored in formal computer science, but let us ignore those finer distinctions. Oftentimes, whatever methods you devise based on the complexities of the data and complexities of the method, it is not possible to handle them in an analytical fashion. It does involve computation, and it is best to resort to computing and computers, so that brings in the technology part. So, in a nutshell, when doing data driven science, one has to deal with these three domains, and so some sort of expertise, varying degrees of expertise in all three domains, at least at the level of understanding, is helpful and necessary to be able to do good work. Just saying that I am a computing expert and I do not want to, I can safely ignore the other two domains is not advisable, although it can be managed with a multidisciplinary team in a multidisciplinary setting. But then also to be able to model things at this level of operation at the methodology domain, you need to understand a little bit about the problem domain and also about the computing aspect. So, so if you think of this, astrostatistics is basically reasoning about astronomy and astrophysics based on data. So, it is data intensive science, data driven science as applied to the astronomy and astrophysics domain. This is how one can summarize astrostatistics. There is also given, I mean, this is a trend in almost all the fields of technology and science, that over the past few decades the data sizes have been soaring up in an exponential fashion. So, this also brings in the so called big data component, where the computing aspects become even more important, the technology part becomes even more important, because larger amounts of data bring in problems related to storage and retrieval, search, and actual computing, dealing with very large numbers of entities. So, because of data rates soaring up over the past few decades continuously, with better precision in instruments, better ability to grab data from make measurements and grab data from your instruments, this aspect of computing is getting more and more important. But again, all three aspects are important for astrostatistics. In fact, let me just end this thing with an interesting summary of what has been happening over past 2.5 3 centuries. This is an interesting perspective by Bradley Efron. In this view, 19th century was dominated by large data sets but simple questions. 20th century, the last century, was dominated by small data sets but again simple questions. This is the century where data sets are large and the questions are complex. So, let me end with that note here.